Okay, the recording has started. Hello, everyone. Good morning, good evening, good afternoon, wherever you are. So here is with our second GeoVirtual event from Gulf Geotechnical Engineers, together with the GMEC, the Geotechnical and Material Engineering Committee from the Society of Engineers in UAE. Allow me to introduce the moderator for this great session, which have great keynote speakers and principal and guest speakers as well. Uh, with us, Dr. Zahid Khan. He is a senior geotechnical engineer and seismic design lead in AECOM, Canada. You will see Calgary and in Calgary office, and he has over 25 years of experience on a variety of civil engineering projects that involve static and dynamic geotechnical engineering services. He also served as an associate professor in geotechnical engineering for 15 years at the American University of Sharjah in UAE. Dr. Zahid has considerable experience in seismic and dynamic earthquake analysis for sites and dikes and dams and soil structure interaction and dynamic liquefaction analysis using advanced constitutive soil models, geophysical testing, response analysis of machine foundations, dynamic testing of piles, and dynamic characterization of materials in laboratory with modified stock type resonant column device, cyclic direct simple shear test, cyclic triaxial, and bundle element. He has published more than 30 journal and several conferences articles. Without any further ado, ladies and gentlemen, with us, Dr. Zahid, over to you to introduce our speakers and the program, and if you want to shed a light on the GMEC as a committee.
Thank you, Hamza. Welcome everyone on this forum to the second GeoVirtual conference organized in collaboration with Gulf Geotechnical Engineers and the Geotechnical and Material Engineering Committee of the Society of Engineers. The spearheads for the Geotechnical and Material Engineering Committee of the Society of Engineers, Dr. Ghanem Kashwani and Dr. Marwan Alzai. I want to congratulate them, and I also want to congratulate Hamza for organizing this conference. I welcome the audience that are present here for to listen and learn from our distinguished speakers. I also want to thank the viewers that are present in the gallery for that. My greetings to you and Assalamu alaikum. Good morning, wherever you are. So it is really my honor to be among very distinguished speakers for this conference. I welcome Professor Alessandro Mandolini, Dr. Ahmed Mufty, and Dr. Julian Seidel. I will introduce them as we go through the schedule in more detail, although Hamza has introduced me a lot. My name is Dr. Zahid Khan, and I will try to introduce the speakers in more details as we go forward. So the program includes a keynote speech from Professor Alessandro Mandolini. Apologies if I'm not pronouncing the name properly. It will be followed by a presentation from Dr. Ahmed Mufty, and last we will have Dr. Julian Seidel as our last speaker. We will have about 40 to 45 minutes for the keynote, followed by about 20 to 25 minutes for Dr. Ahmed Mufti, and a brief and short 15-minute speech by Dr. Julian Seidel. So, and then we will have a question and answer session for 10 to 15 minutes at the end. Okay, so let me introduce you our keynote speaker, Professor Alessandro Mandolini. It is with great honor to welcome him. He is the full professor of geotechnical engineering, head of the Department of Engineering at University of Campania, and he is also member of the Academic Senate at University of Campania. He is the chair of the Deep Foundations, ISSMGE, and chair of the Italian Geotechnical Scientific Community. He has a huge experience in both professional practice and also as a academician. His research is well cited, and he has a lot of distinctions and international recognition of his scientific work as member of several societies and professional organizations. Today, he will enrich us with his presentation, and I welcome Professor Alessandro Mandolini, and over to you, Professor.
Thank you. Thank you very much for your kind introduction. First of all, I want to thank the organizing committee, in particular my friends, Mr. Hamzah Al-Hashemi, because inviting me for this very important and impressive event. I am very honored. I hope to be at the right level for the audience. I will share my screen in order to start with my presentation. Okay, as you know, the title of my presentation is Design of Pilot Foundations. I will try to focus my attention on some critical aspects about the design of pilot foundations, and in particular, the outline of my presentation will be, after recalling some traditional approaches to the design of pilot foundations. For the reason I will try to explain later on, I will focus my attention on the shaft resistance of piles. Then I will give you some examples, and then I will draw some conclusions and suggestions for your future activities. The first point we have to take is to recall us what we as foundation engineers typically do when the decision of using piles has been taken. It means that I will not deal with all the problems related to select the right type of foundations depending on the structure, on the soil conditions, and economical aspects of a design that you know is a very complex matter. I will try directly to go to pilot foundations, assuming that all the thoughts about why we are selecting the piles have been analyzed and the decision has been taken. Typically, in a traditional design approach, we focus our attention on the single pile response to vertical and horizontal loads in terms of bearing capacity and movements. Here you can see a typical load settlement relationships coming from some experiments on single piles. Then we try to extrapolate the behavior of single piles to the group by considering the interaction among piles, both when approaching failure, I mean looking at a single pile failure or row of piles of bulk failure of mechanisms, and then under design working loads, because we are requested to give our estimate of vertical and horizontal displacements, rotations, and so on, in order to be sure that under working conditions, all the limit states are fulfilled, and behavior and the expected behavior of a structure is satisfied. Obviously, as you can imagine, the topics are very, very, very are several, and I think is not the case to say everything about all the possible aspects related to the design of pilot foundation. Here I have put on the screen some reference when I was asked to deliver a keynote lecture in the occasion of the Geotechnical International Conference in Hanoi. You can download the paper, is an open access paper, in order to have a more larger view about all the topics I will not deal with during this presentation. What is very important in any case to recall is that the prediction of single pile response to loads is a fundamental step of the design process, because we are always asked to predict in a better way the response to the load. And we are must aware about the fact that any error concerning the prediction of the behavior of the single pile is reflected, if not amplified, in the prediction of the behavior on the entire pile foundations. That means we must be very careful when dealing with single pile response to load, because the reliability of our design is strictly depending on how reliable is the prediction of the single pile. And I have noted, and the paper I mentioned before is in some way a proof of that, that in recent times, rarely the efforts of the scientific community have focused on the single pile. In the last year, we have seen a growth of methods concerning pile groups, pile drafts, but about single pile, it seems to me that the accumulated knowledge in the past was considered enough to proceed. It's not my personal opinion, so I think we have to go back to the single pile in order to improve our capability to correctly design a pilot foundations. So if we concentrate our attention on the vertical loads, because it's the most typical loading condition on pile groups, on pile foundation, sorry, as all of you knows, the load is resisted, the applied load at the head of pile is resisted by shaft friction, Q sub S, and normal stress at the pile base, Q sub B. And the two unit resistance are mobilized by very different mechanisms. The first one, the shaft friction, is mobilized by sliding mechanisms occurring at the soil pile interface, while the second one, the base resistance, is mobilized by punching mechanisms occurring at the soil pile base. And these two different mechanisms implies that the required movements are very different, few millimeters for the sliding mechanisms along the pile shaft, and some percent of pile diameters, that mean centimeters, if not tenths of centimeters, that means 1 or 2 order of magnitude larger, for the punching mechanisms at the pile base. But before pile base resistance is activated, very often, except for a very particular case, pile shaft resistance is partially, if not fully, mobilized. And it is very important, because if we go through our experience accumulated over the time, here you see the map, the area map of my city, and in the past we have collected more than exactly 125 pilot tests on different piles, driven, screw, continuous flight augers, and bored, in rather uniform subsoil conditions. And as you can see, the pile diameters are ranging between 0.35 meters and 2 meters, the length from tenths of meters to 42 meters, a slenderness ratio from about 15 to 60. And all the results we get, here is shown just an example, are giving us the same information. That is, if we perform a load test on a single pile and we define conventionally the ultimate resistance of a single pile as the resistance corresponding to some settlement, very often in Italy is by law, as in Europe by Eurocodes, the 10% of pile diameters, you can read on the single pile load settlement curves the final ultimate value that in the example is 3.2 meganewton. So if we look at some working conditions, for instance, at a load of 1.2 meganewton corresponding to a global factor of safety of about 2.7 for this pile, but the same is for the other 124 piles, what we observe that all the load is transferred along a reduced pile length, that is an active or critical pile length that can be estimated very simply by this simple equation. And it means that under working conditions, the pile response is ruled by pile shaft. And please remember that due to the sliding mechanisms occurring at pile shaft, this resistance is mobilized at few millimeters. That means, again, that if we apply a load below the shaft resistance, the expected settlement of the single pile will be proportionally smaller than few millimeters. That means small settlement. That means even if amplified by group effects due to interaction among piles, presumably the settlement of the pile group will be acceptable and serviceability limit state will be satisfied. Obviously, the implication for design is that in order to be sure that we are applying on the pile a load below the shaft resistance, we should have a correct evaluation of the shaft resistance. Otherwise, we could be wrong. This is the reason why I will continue my presentation focusing on shaft resistance and starting from the important statement made by Terzaghi in his very famous book, Theoretical Soil Mechanics, written by the father of soil mechanics, Professor Terzaghi. And in some page, he stated, our knowledge of the influence of the method of installing the piles on the skin friction and on the intensity of the shearing stresses is still rudimentary, and the prospects for evaluating this influence by theory are very slight. Clearly, it is a statement of more than 80 years ago. So maybe some steps forward are available now. And if we go to the way in which we evaluate the shaft resistance by methods based on soil parameters, typically we assume that the skin friction is proportional to the normal horizontal stresses acting along the pile shaft at failure, sigma prime RF, affected by some friction coefficient, tangent of delta. And typically, what we do is to put that to assume that the horizontal stress at failure is proportional to the vertical effective stress by some magic parameters K that depends on the pile type and the soil type. For instance, here you can see a table given by Poulos, Cartan, and Sboul in their state-of-the-art reports delivered in the occasion of the 15th International Conference of Soil Mechanics and Geotechnical Engineering held in Istanbul in 2001, referring to the indication given for piles, bored piles in sandy soils. We look that they resumed the suggestion by Yasupuku and co-authors in 1997, but apart from the indication, they focus their attention on the fact that the key values are depending on the friction angle, phi, by the passive coefficient Kp, and by the at rest at pressure coefficient K naught, the latter being influenced also by the overconsolidation ratio, as we will see later during my presentation. If we go in a recent book, I could say recent, but is 13 years ago, written by Vigiani, Russo, and myself, still referring to sandy soils, you see a lot of key value given for different pile types and depending only from relative density. So if we put together the two indications we have from literature, as you can imagine, there are a lot of other indication, but more or less all these indications are based on the same fundamental parameters, that is the friction angle, the overconsolidation ratio, and the relative density of the soil, if we are dealing with coarse-grained soils, but sand in all the tables I showed you before. So I appreciated very much what Professor Randolph from University of Western Australia stated is one of the last sentences in his ranking lecture held at the Institution of Civil Engineers in 2003. If we are to continue to attract the best of each new generation of engineers, and you are the best of each new generation, then we must incorporate science in our teaching and our practice, using empirical approaches to validate and calibrate, but not replace scientific theory. In some way, Professor Randolph is supporting the idea that empirical methods are good enough, especially when dealing with piles, but empirical methods should be based on theoretical consideration in order to be understood and to be rightly driven to give their best results. In other way, we could say that scientific approach to estimate shaft resistance should be based on all those factors considered relevant, as derived from wide theoretical and experimental researches. So, if we go in more detail, and so we restrict our focus on the shaft resistance of bored piles, typically the ratio K over K naught is considered as a measure of the stress change induced in the soils as results of the pile construction. It is not true. It is wrong. as we will see later during my presentation. First of all, when dealing with borer piles, we know that the interface among pile and soil is such that the slip surface is obtained by enveloping all pile asperities, then resulting in a failure occurring in the soil. That means at the soil-soil interface, that means that the friction coefficients, depending on some value delta, can be assumed without doubts as the friction angle of the soil. The problem is the key value. And if we look at the experiments coming from all over the world, we know that if we are looking at poorly constructed borer piles, this ratio is typically lesser than 1, rarely lesser than 2/3. For well-constructed borer piles, that means I install borer piles without changing the state of the stress into the soil. This ratio is about 1, and if we are installing a continuous flat auger piles, this ratio, depending on the equipment parameters adopted during the installation, that is the rate of penetration of the screw into the soil, as well as the rate of revolution, we could obtain also ratio up to 1.5. But assuming a classical bored pile and a classical well-constructed bored piles, as we must do when designing, because when designing we cannot assume that the pile will be constructed in a wrong way, we can assume that the key value is equal to keynote. And keynote is the earth pressure coefficient that, according to main Equalawi, can be related to the friction angle of the soil and to the overconsolidation ratio by this simple relation. K naught is equal to 1 minus sin phi times OCR at power sin phi. And this value clearly should be lesser than the passive coefficient of the soil, Kp. But if we look at this relation and we consider a normal consolidated soil, sandy soil, we have that independently from the friction angle value, ranging from a sand from 27 degrees to 40 degrees, the beta values, that is the product of K naught and tangent phi, is almost constant, because K naught is a decreasing function of phi, tangent phi is increasing function of phi, and for this range of phi, the product is constant. That means for normally consolidated sand, we should have a beta value of the order of 0.3, always of the order of 0.3. But if we look at some collected data published by Chen and Equalawi in 2002, coming from 100 static load tests from 53 different sites in the United States of America, with pile length and diameters ranging in a quite wide range, as you can see, we have a large scatter of the data. But what is important to stress is that all the data are larger than the predicted value for normally consolidated soils. Is it only OCR effect? This is our questions. I will try to give an answer to these questions. There is another important research work made by Rees O'Neill in 1999. For sense and gravely sense, they suggested us to assume this distribution of beta value with depth. It is called beta Z value, the method, sorry. And some years later, Rollins and co-authors extended the method for gravels. So you see that we have three different curves depending on the soil grading. And the soil grading appears for the first time in these very common design methods, but all the methods we have seen before dealt only with the phi, OCR, and relative density. But since this method is based on experimental data, probably an important role is also played by the soil grading. So we try to understand, and to understand, I will use this video that my friend Rodrigo Salgado from the United States gave me during some experiments we carried out under a common research. And you see that during the sliding mechanism along the pile shaft, there is a thin soil cylinder coaxial with the pile involved in the failure. This is called shear band, and the thickness of shear band is a function of the soil grain size as represented by the diameters of the grain size at 50% D50. And some researchers, you see the name in the slides, suggested that larger is D50, larger will be the thickness of the shear band by a coefficient n, that is ranging between 5 and 13, depending on D15. But no operative suggestions are given. So for the design, we don't know if we have to assume 5, 10, 20, or some other numbers in order to understand the thickness of the shear band. And the thickness of the shear band is very important. Recently, my PhD students, carrying out a broad literature review, aimed to establish the relation among the thickness of the shear band and other physical properties of a sandy soil, like grain size distribution, not only D50, but also the coefficient of uniformity. In the figure in the low side of my slides, on the left side, you see that we can have the same D50, but two very different coefficients of uniformity for the sand. And depending on the shape of the grain sides, in some way related to the friction angle at critical state, as you can see, as you know, is possible to define a relation giving us how to estimate in a rational way the coefficient of proportionality n in order to obtain the thickness of the shear band from the physical properties of the grain size of the sand soil. I was saying that it is very important. Why it is very important? Because due to the formation of the shear band and due to the dilative behavior of the soil, the shear band will determine an outward radial displacement against the soil mass not involved in the mechanisms. And we tried some years ago to understand from numerical point of view how this is important. And without going into the details of the numerical analysis, you can have the paper on the American Society of Civil Engineering journals and ACTA journals. The method was validated also against the full-scale static load test on instrumented piles belonging to our files. And we got a rule to estimate the movements, the radial displacement U, depending on the shear band thickness Ts and the tangent of the dilatancy angle at peak as defined by the Bolton dilatancy theory published on Geotechnique in '86. And it is very important because dilatancy always occurs, at least at shallow depth. You know that dilatancy is a mechanism occurring as a function of the relative density and mean stress. At shallow depth, mean stress are very low, and also a loose soil can dilate. So dilatancy always occurs depending on the relative density and mean stress. Dilatancy can play an important role over a reduced pile length or all the pile length if the soil is dense or over-consolidated. And due to this dilation, the soil mass will react during loading, not during construction, as stated before, but during loading by increasing the horizontal stress, and the increase will depend mainly on the soil stiffness. So we could say that the dilation of the shear band triggers the involvement of the soil stiffness in the interface response in order to develop the skin friction along the pile shaft. All the methods we have seen until now are very often not considering soil stiffness for determining soil resistance. In this case, pile soil resistance. So we have a coupling of the stiffness and resistance in developing skin friction along pile shaft. If we consider these very simple methods based on cylindrical cavity expansion, and for sake of simplicity, we refer to the elastic assumption, the stiffness of the spring along the pile shaft can be simply obtained by this formula you see here. But considering that very often the thickness of the shear band is very small if compared to the pile diameter, we can simplify the formula by this equation in which the stiffness of the spring along the pile shaft is related not only to the soil stiffness but also to the pile diameter by this equation. By combining all in the fundamental equation for the skin friction, where we have not only the original state of stress, but also the increase of the stress into the soil due to dilation proportional to displacement U, we get this equation. In the PhD thesis, the guy I mentioned before, Cesaro, carried out a broad parametric studies by using a cylindrical cavity expansion, but a more refined model, elastoplastic, as suggested by Ya and Asby in 91. And he carried out more than 600 cases, ranging the stiffness ratio, the friction angle, the dilatancy angle, and he found that until the displacement at pile soil interface is lesser than some yielding value related to the stiffness ratio and friction angle of the soil by this relation, the stiffness, the engaged stiffness of the soil will be the small shear stiffness of the soil. But if the dilatancy will determine an outward displacement larger than this value, the stiffness will decay by following this very simple formula. So, if you want to summarize what we have presented here, typically when dealing with piles in coarse-grained soil deposit, we have no availability of lab tests on undisturbed soil sample because the impossibility to retrieve undisturbed soil sample in this kind of soil, apart from very, very particular techniques. So we typically use the results of in situ tests, CPT, SPT, seismic profiles, and so on, to estimate the relevant soil parameters, that is the unit weight of soil, the friction angle, the over-consolidation ratio, the relative density, the shear stiffness at a small strain. But we can also perform lab tests to estimate intrinsic, let's say, soil properties, like friction angle at critical states. We can perform lab tests on disturbed soil samples to estimate FCV, and very simple and basic soil grain size distributions to get D50 and coefficient uniformity. So for a given pile geometry, that means for given pile length and pile diameters, we could follow the following procedures by keeping in our mind that the reference formula at a given depth Z is what shown in the below part of the slides. So we need all those parameters in the upper part of the slides. First of all, we can estimate keynote by using the main and Culloway relationship. Then we can estimate the mean stress at depth Z, then involving the unit weight of soil, total or submerged, depending on the water condition. Then, by the relation I showed you before, we can estimate the shear band thickness depending on D50, FCV, and coefficient of uniformity. And then, by bolt-on theory, we can estimate the dilatancy friction angle at peak. Then we can estimate the outward movements due to dilatancy, estimate the yielding outward movements, and then, depending on the movements, we can use a J0 or a reduced value of shear stiffness, considering in an equivalent elastic theory the reduction of stiffness due to soil nonlinearity and plasticity. It seems that we were not using the relative density as suggested by other authors, as I recalled in my first slides. But if we are using boson theory, as you know, we are considering the relative density because the friction angle of the soil is related to the friction angle at critical states as a function of the mean stress acting at a given depth and the relative density at the same depth. That means, in some way, in this friction angle phi is included not only phi CV, but also the relative density. Then I suggest you to use always boson theory to check if the values coming from some correlation that you know are established on the basis of some, for a specific site, a specific soil deposit. So it's not sure that it is valid for our specific site conditions where we are designing our piles. But in any case, this is my personal suggestion. In any case, it is important to stress that the relative density is included in our fundamental parameters for the methods I am proposing here. So, coming back to the previous slides, is only OCR effects the reason on the basis of which we are looking this scattering? No. There is an increase of the skin friction as measured by delta beta due to some of the factors suggested by the authors I mentioned before, Poulos and co-authors, Vijani and co-authors, but by others, also by other factors like the stiffness ratio, the soil grain size distribution, D50, and coefficient and uniformity, as scaled by the pile diameters. I will give you a comment in the next few slides because I'm going to conclude. But before to conclude, I want to show you the application of the method in the occasion of the international experimental sites for testing we organized by the TC212 Technical Committee of the International Society for Soil Mechanics and Geotechnical Engineering. I am chairing until now from 2050. In 2017, we organized this international prediction event, and we performed a lot of pilot tests. I don't want to go into details. I just look at the results on one of the piles, not because it's the better, but because it's one. All the results are repeatable for all the piles, bored piles, belonging to the experimental sites. We are in a fine silty sand deposit with a D50 of 0.19 millimeters. That is the average value of 23 samples taken during drilling the soil. And it is, first of all, very important to note that these blue curves you are looking here are the 94 predictions made by experts, international experts from 13 different countries. Please note that there is a scatter of one order of magnitude among the international community in predicting the behavior on a single pile in a very well-known soil deposit, because as you can imagine, it was very deeply investigated in order to give to the predictors all the informations they need sorry, they need to make their best prediction. But the results of the loading test gave a different results. The shaft resistance was 1,120 kilonewtons. So, in these figures, I reported the prediction made by the so-called FHW method in 1999, that is the method based on the beta curve I showed before, and the so-called FHWA 2010 methods that is based on Kuhlawi and Main proposal taking into account for OCR. They are not wrong. They are simply considered one of the aspects playing a role in the mobilization of the skin friction. The so-called 3M method, that is the method we proposed some years ago, is just coupling the influence of the state of stress via keynote, of the over-consolidation ratio, OCR, the friction angle, phi, but also the dilation at pile soil interface, depending on the soil grain size distribution as discussed earlier. So, summarizing, if you want to apply the method at a given depth, please estimate the at-rest horizontal stress. Then try to estimate the change due to the pile construction. Is not simple, is very difficult task. But we are asked to do that. If we assume that the pile is well constructed, we are dealing with ball piles, we can reasonably assume that this change is almost equal to zero. Then, during the loading stage, since a shear bend develops at pile soil interface, we must estimate its thickness by taking into account soil properties, physical intrinsic soil properties, D15 and coefficient of uniformity, and particle shape as represented by friction angle at critical states. Then estimate the outward movements U in order to evaluate the increase of the horizontal stress in the soil while approaching the failure during the loading stage. And then at failure, you will have how much is the true, let's say true, horizontal effective stress acting on the pile surface from the value of which the skin friction depends. Please note, very important, that is not important how much the outward movements is. Is not important how large the pile diameter is. Is important how much is the ratio. If we have large diameter bored piles, that means large D, in a very fine sand, that means small D50, small TS, and then small u, the dilation will play a negligible role. On the contrary, if we have a small to medium pile diameters in a coarse soils like a medium to medium sand to gravel, the dilation will play a fundamental role in developing skin friction, and it is not considered until now. And it is very important because very often we perform load test to failure on a pile with a smaller diameter but instrumented in order to measure skin friction and to assume that the same skin friction will be available at the pile shaft interface with soil with a pile with a larger pile diameter. It is not true because the pile diameter is playing a role on the dilation, as I tried to demonstrate. So, concluding remarks. I think that perhaps culpably we have forgotten that our weak point is still the single pile, not only as in Terzaghi's times, but now it is still true. And I also understand that we love empirical methods because they are easy to use and they are presumed to be accurate because the values, the empirical values we put in empirical methods are coming from experience. So we trust in them. But please consider that if used as a black box for any pile, for any soil, independently from the soil grain size distribution, independently from the dilation potential of the soil and so on, they can lead to significant errors. So, according to the statement made by Professor Randolph in his ranking lecture, I think that the best empirical methods is one developed from theoretical considerations, then calibrated using experimental data with few, preferably, parameters of a clear physical significance, therefore measurable, and not just numbers, as we are typically doing in our daily practice. So the last slides is not my personal opinion, but is an opinion expressed by Maxwell, that you know is the father of the theory of electromagnetic radiation, and well-known equation Maxwell's was the base of the unification in physics, the second great unification in physics after that realized by Newton. So Maxwell, probably thinking to piles, I'm joking, said the success on any physical investigations depends on the judicious selection of what is to be observed as of primary importance, combined with a voluntary abstraction of the mind from those features which, however attractive they may appear, we are not yet sufficiently advanced in science to investigate with profit. That means I'm not sure that other parameters could be relevant. I'm just saying that please start to include those parameters we have observed to be of primary importance. Then we could work on the, let's say, secondary parameters on which we have not still clear idea on that. If we continue to use empirical methods in a black box way, we will be wrong and we will not allow to our discipline to give the right contribution in the field of civil engineering. Thank you very much.
Thank you very much, Professor. It was really very nice presentation. I'm sure the listeners, myself, and others are as anxious to ask you questions, but we will have to reorganize our thoughts about the presentation and ask the questions at the end of the presentations from the three speakers. So if you can please write down your questions so that you don't forget it. And I'm sure you will have a lot of questions, as I have too. Again, thank you very much, Professor Alessandro Mandolini. Thank you very much for honoring us and giving us such a great summary of the recent advances in deep foundations design,
Thank you to all of you.
especially related to the shaft resistance. Okay, so let's move on to our other distinguished speaker, Dr. Ahmed Mufty. He's a well-known practitioner and also academician. Dr. Mufty has worked as technical manager of HSSG and later with APCC, which are the two of the largest foundation companies in the UAE. He is very well experienced in the design works for shoring, deep excavations, and pile foundations, and he has been involved in providing services to over 100 iconic projects. He worked in Iraq, UAE, Qatar, Oman, India, and Canada, and he has delivered several courses on soil mechanics, numerical analysis, and geotechnical engineering at both undergraduate and postgraduate level. He has supervised postgraduate students and have authored more than 30 articles and published one book. He's currently he's currently leading the software development team with Rock Science that makes very famous software. And since we just talked about piles, so two of the most important softwares of Rock Science Group are RS Piles and Settle 3, which I'm sure most of us and in the audience have used it. So Dr. Ahmed Mufty will present the ACI provisions for structural design of board piles, especially related to ACI 3118, ACI 336, and ACI 117. It is my honor to welcome Dr. Ahmed Mufty.
Thank you, Dr. Zahid. I'm blessed and honored to be with you all. It is an honor to present with GeoVirtual, which is a promising and a very successful platform with the passion that Hamzah has for this geotechnical engineering subject in general and pile foundations in special. I'm sure that everybody here was interested in what Dr. Alejandro presented because everybody is familiar with shaft friction and how to calculate shaft friction in sand. So the addition was valuable. I will start sharing my screen to start my presentation, which is completely different from this story. So Dr. Zahid forgot Saudi Arabia. I worked in Saudi Arabia also, and I still have some work there going on with one of the major projects. I was a university professor for continuously 9 years and separately 12 years. Then I moved to UAE and I worked in piling and shoring. And so I faced these design issues and design problems, but the amount and the substantial amount of changes and developments happened in the last decade in pile structural design, especially in the European part and in the ACI, American Concrete Institute part. are really confusing designers, and they need to follow every single day what's going on. ICE is publishing, Eurocodes are getting published, ACI is renewing every 3-4 years their committee codes. And also I have a personal contact with some professionals. They are like in the Canadian Geotechnical Society. We just published the Canadian Foundation Engineering Manual 2023. And there is DM7, which is Design Manual of the naval facilities before. Now it's gone to the unified unified something, I don't know, I forgot the name. So DM 7.1 is published and DM 7.2 is getting published. And I'm authoring a book. I'm writing a book with 2 other professors about foundation engineering. And we were working on the structural design part. And I found out that in 2014, I was working in 2017, I was working in UAE, and I used 2014 ACI code. And there was a very big problem in shear calculations when there is an axial force. In 2019, we overcome that problem, and it is solved because the whole system of the code has changed. And again, new problem came with the shear calculation of the foundations, shallow foundations especially. So I got confused a little bit. I said, let me wait until 2025 is published, then I finish the book. And fortunately, this lecture became after the issuing of 2025 ACI 318, which was published 11th of this month. So it's about 17 days ago. So my presentation is about ACI provisions for structural design of board piles. Anybody who is familiar with Eurocodes and ACI code, he will immediately start comparing what's going on here. I will not compare with Eurocodes. I will just present what I have collected from the important codes related to structural design of board piles. And of course, the material is so huge, I can't finish everything in 30-40 minutes. So at least we will cover most of the important parts. So we're going to talk about the provisions in the following codes: ACI 31825, which is just published, ACI 722, 2022, ASCE 7, which is related to loads on buildings and foundations and etc. American Concrete Institute 336.3. This is in 2014, published 2014. ACI 336.1, 2001. And ACI 336, now the name became ACI Spec 336.1R in 2024. And of course, ACI 11710. 117, I think the other one is 20 or 22. The changes, it's not really related to piles. What is applicable is in 11710. Let's start with pile loads. I'll go a little bit faster here because my time is limited. So we have two types of loads, service loads on piles and ultimate load on piles. So the service loads, let's forget about the envelope loads because everybody designs as one load coming from the envelope and design with a factor multiplied by that load and goes directly to the reinforcement and the proportioning of the section. We will do here the correct scientific method, which is following the serviceability limit state loads at service loads. So the service loads in ASCE 7 2022 are combined in this table. So D for dead load, L for live load, W for wind load, E for seismic load, T for thermal load, H is usually the load that is generated from ground movement or ground load, like earth pressure, like groundwater pressure, like this. The most important here, you need to know that W, the wind load, and the earthquake load are not as service loads anymore. They're not service loads. They are ultimate loads now. They are factored loads. So whenever you calculate based on the new standards, you're calculating factored loads. And this is very important because most of the designers, they forget this issue and they calculate service wind loads, then multiply by a smaller factor to get the service load. And this will end up with lower loads than real required ones. I named the load roof load or the snow load or the rain load as PS. Service, some service P. So we have the these combinations until from SLS1 to SLS13, they are taking all considerable loading conditions that can be applied in a service state. And you can see some of them I'm writing maximum, some of them I'm writing minimum. So when you check, it's like you need to check whether it is uplift, so it's a tension on the pile, or it's a minimum compression, or it's a maximum compression. So when I say maximum, it's a maximum compression. You need to check all these loads at service limit state. In fact, not all of these, or we can ignore these if we are talking about geotechnical considerations. But for structural design, these are very important. Like if you want crack width, if you want stresses in the reinforcement, if you want durability, you need to take these loads into consideration. The geotechnical part of the service loads, they are based on ACI 336 and not ASCE 7. Of course, ASCE 7 is important here because ACI 318 does not have service loads anymore. It refers you to ASCE 7. So here you can see we are checking with the factors with factors of safety. So you calculate QB ultimate, the base resistance or the end bearing resistance, and the QS ultimate, which is the ultimate shaft resistance. And you check the service load in this table as shown, each one with a different checking capacity. So you have 3 factors of safety here. I usually use 4. So first factor of safety is for the QB ultimate, so it's for end bearing. FS2 is for skin friction. FS3 is a combined factor of safety for both. In fact, there is a possibility that you can use another factor of safety only for skin friction. You ignore the ultimate end bearing in the long piles. So if you have a long pile, there's no meaning to add end bearing resistance to the capacity of the pile, because you will never reach to the base with any load. So you're not transferring any load to the bottom. So you should not take the base resistance in the capacity. At that time, you need another factor of safety, which is for QS ultimate alone. There's no QB ultimate with it. Usually FS1, FS2 are like this one usually is between 3 and 5. This one is between 1.5 and 2. And if it is alone, it should be around 2.5. And the factor of safety 3 is usually 2.5 for the overall capacity. And you can see I'm putting like downward for the earthquake and wind load to add to the load, so that you can have a maximum compression. And I'm adding also the negative skin friction here as required by the code ACI 336. In fact, ACI 336 is allowing to increase the capacity by 1.33 if you have earthquake or storm or wind load. But the new codes are not really interested in increasing the capacity. They prefer to use the original capacity. In ACI 336, they use the weight of the pile with the dead load as a DG, D gravity. This is used for countering the uplift load or the tension load on the pile. As I said, W and E as the previous service loads. Here we are following ASCE 722 loads, so the equations are a little bit different than the ACI 336 because it's old. And that's why you see there is 0.6E, 0.6W, and multiplied with another factor, reduction factor 0.75. So this 0.6 and 0.6, it's like you are dividing 1 over 1.6, the ultimate load factor of 1.6. So this is for your information. I can't go through every single detail here, but you can make this summary. And by the way, in the Gulf, you can see also another set of service and ultimate loads combinations. For example, in the Saudi building code, they're different a little bit. So when I design something in Saudi Arabia, or I may need to add those combinations also. So a huge amount of combinations. Before, it was very difficult to do all these combinations, but with the presence of Excel sheets or software like the software like Araspile, you can add as many combination as you want, and you solve the whole project piles for full number of combinations with one click. Well, yeah, it takes time until you get the results, but you can have fun, watch TV, drink some coffee until it finishes. Maybe you need to sleep sometimes. Let's see some notes from ACI 336.3 2014. So when the length to width or length to diameter ratio, I will use B in my presentation because you should remember that piles may be circular and may be rectangular. So if it is rectangular, B is the smaller side length, which we call it the breadth. So L over B, whether it's a diameter, whether it's the breadth, if it is less than 10, the piles may be considered rigid. If it is greater than 10, may be considered flexible. These are important for lateral analysis and lateral considerations. And ACI 336 also allows you to use I gross multiplied by modulus of deformation of the concrete. And the design steps, of course, you need to determine the pier dimensions, which is diameter and length, or breadth, width, and length, and design of concrete pier element and any necessary reinforcement. Skin friction is developed as a settlement of around 3 to 10 millimeters, around 1% to 2% of the breadth, while end bearing usually develop as settlements around 3% to 5%, and to reach real ultimate conditions, you may need to reach 10%. Ultimate loads on piles are taken from ACI 318 to 2025. So these are 7 main combinations, and you can see there is a combination for earthquake and combination for wind. We are not replacing them, so each one has its own combination. And the E, which is the earthquake forces, may be horizontal and may be vertical. So if it is vertical, you may need to add, you may need to subtract instead of adding. And the effect of the fluid is not the effect of groundwater. So we need to distinguish these two from each other. They are both fluid, but this is coming from H, the groundwater effects, or the earth pressure effects, and F is coming from fluids like a storage tank, like a swimming pool, like any pond or something within the building. So these F should be taken into consideration carefully, because if it adds to the primary load and it is permanent, so you need to add it to the dead load, and it will be multiplied by the factors of the dead load. If F is countering the main loading case, here are the main loading cases. So each equation of these has one major component. So if F is countering the major component, you need to take you need to take it less than full. This is one. And if it is not permanent, better not to take it at all. So if not permanent and counter effects, do not add F. The negative skin friction is important. So sorry, this one is not negative. This is the snow load. The other one was there in the ACI 336 was the skin friction, negative skin friction. So this is the snow load. Again, in the new ASCE ACI, calculated as factored load, like the wind, like the earthquake. You can also decrease the live load by half if you have anything less than 5 kPa, and it should not be in garages or public areas. So you can decrease the live load to half. If W is at service load level, then all factors shall apply, 1.6 instead of 1 and 0.8 instead of 0.5. So you can see here, for example, we are using 1 for the wind load. So don't get confused. This is already factored load, calculated as a factored load. The new calculations are like that. If you calculate as the old style service load, you need to multiply this by 1.6 instead. Now we're talking, this is important part I'm talking about, which is the earth pressure and the groundwater. So where loads in the old ASCE or ACI, H was taken as 1 unit. So even groundwater is not like earth pressure. You know, it's 10 meters groundwater you have. So why do I multiply by 1.6? That was the question I always ask myself. Now in the new recommendations, they changed. They divided the H into HEB, which is coming from soil, and HW, which is coming from groundwater. So now the groundwater is, the load factor of the groundwater is different. It's not 1.6 anymore. And this is a huge difference, in the new loading system. And also you need to take care about the groundwater effects, if they are countering the maximum effect or the main effect or not. You should treat it like the fluid. If it is permanent and having a minimum, a permanent elevation, then you can include it with a factor of 1. Otherwise, you should not add it. Like if it is a fluctuating groundwater, you should not add it to the equations if it is countering the effect. If it's not countering the effect, you need to take the maximum groundwater level that time. I'm talking here for piles. Of course, if you have the water behind the retaining wall, that also causes a pressure on the retaining wall. And if that retaining wall has a base or has a foundation that is resting on piles, then again the piles will take the effect of this lateral groundwater pressure. I'm moving to tolerances. So in ACI 117 and ACI 336, there are some tolerances. I will go through some of them, or maybe most of them. So area or diameter. Before, ACI 336 was allowing less area than the pile area. So if you have a diameter of 1,000 millimeters, that will give like around 0.76 something meters squared. We could have, if you have a less diameter after construction, you could have passed that pile. Now, no, you should have a minimum of 100% area. If not, you need to redesign that pile. In ACI 117.10 and ACI 336.3, there is something called clean out. In the clean out, at the bottom of the pile, you need to have some debris is there. The maximum debris area that has 5 centimeters thick spoil should not be more than 10% of the area of the pile. In the same time, the ACI 336.24, not 14, this is 2014, this is 2024. In 2024, they asked and added 2 items for the bottom they want this to be level to at least 1 to 12, vertical to horizontal. And they need also the rest of the area should be not having debris more than 12.5 millimeters, which is half inch, and it should be greater than 50% of the total area of the pile. So two conditions you need to check at the bottom of the pile. Shift. Oh my God, the shift. This one is a headache for structural designers of piles, of board piles, because location shift means extra moment. An extra moment will need more reinforcement, and that reinforcement, if you calculate like in every pile 2 bars more, you're going to hundreds of tons in big projects. Anyway, we should follow the standards, and there is no chance to leave the shift tolerance without approaching it. ACI 336.3 says it should be the lesser of 4% of the diameter of the breadth, or 75 millimeters. ACI 318.25 requires 75 millimeter shift in design. Clearly states you need to design for 75 millimeters shift, the new ACI. If you remember the old ACIs, there was no pile in the ACI 99 or ACI 2005. There was no pile design included in these standards. We were following them as design of columns, but they're not. They were not. There was clear statement in the beginning that ACI Code 318 does not cover deep foundations. But now they included it, and it's part of the foundations chapter, which is chapter 13. The tolerance less than 50 millimeter, is it possible? Yes, it's possible. We can do it. But how can you convince the consultant? How can you convince the client? This is the important part. Because if you can convince the project owner that you can make piles less than 75 millimeters in shift, in position, you will save a lot of money for yourself and for him. And in fact, if the pile is a single pile alone and holding, like, let's say, a pier or holding a column load directly on it, like say the ones for the metro of Dubai. In this case, shift is very important. You can't ignore it, and you need to be very careful to have the pile installed without shift as much as possible, because there is nothing to support this pile. It's a standalone. Location shift in ACI 11710, 2010. This is strange compared to the others, because it allows, or let's say not allows, it recommends that the dimension should not move as an edge. So you have edge displacement. Edge displacement for the compression members if the dimension is more than 2.4 meters, so plus minus 50 millimeters, the edge position. Where dimension is less than 2.4 millimeters, the greater of 2% of breadth, or 13 millimeters, very small, the edge. I don't think this should be applied to piles. Anyway, the above is applicable for piles existing. For example, you have a part of the pile above ground holding a platform or a jet or something, a jetty or something. So the position will be very important, and the edge is very important because you will jacket that pile. Top of board pile, horizontal deviation as cast center shall be the lesser of 4.2% of the shaft or 75 millimeters. This is similar to ACI 336 that we have just talked about. But if you look to 4.2%, you will get this table. So if you have a 600, 800 piles until 1,500 piles, you're talking about much less than 75 millimeters. And I have used this before in my designs. Before ACI introduced 75 millimeters as a must. But still, these are applicable for ACI 11710. It's not superseded yet. We can increase the tolerance and we can decrease the tolerance within our projects, depending on our clients and our consultants, how much they are understanding the behavior of piles. Out of plumbness, so if the pile is straight, so out of plumbness is 0. If the pile is inclined or waving around the main axis, you are allowed up to 1.5%, so 1 over 66.5 in the ACI spec 336.1, 2024. 2024. This is not 2014, 2024. This governs the one in ACI 11710 because ACI 11710 allows 1 to 50. And if you remember our projects in the Gulf region, we use 1 over 75. So this is more than 1 over 75 and less than 11710, which is 150. So I think 1 over 75 is more conservative, of course. You can use the 1 over 75. Not conservative, sorry. It is more strict, 1 over 75. We should follow the 1 over 75. It gives better design for us as piling designers. Why the shift is not important when there are many piles and there's a pile cap? If you see, if you have one row of piles and you have moments and one pile is shifted outside, you will have moment in the other direction. There's no moment in the other direction in the main design loads, but if the pile is shifted, you will create a moment in the other direction. That's why the shift is very important when you have one row of piles or a single pile under a column. You have a column, then you shift it half meter away. The column will not sit on the pile anymore. If you have a group of piles, look to the equation that you can distribute the load with. So the group load divided by number of piles. This is whether you have a shift or not. But the rest of the load comes from the moments. So if moment multiplied by the distance y, then divided by the summation of y squared, you will see this value. If you add here 75 millimeter or you don't add, so this is 3 meter, 6 meter. If you add another 0.07, what will happen? Nothing. This will not change the loads on the piles too much. In my opinion, shift within the tolerances in a huge number of piles in a group. You don't need really to visit that shift and design for it. But what shall we do? If the project specifications are saying, the project specs are saying you should follow ACI 318, you should follow. You should get that 75 millimeter in the design. This is ACI 11710 again. How much the pile is allowed to go up or down. The top surface of the drilled pile, of the bored pile, the vertical deviation plus 25 and minus 75. This is like for the key that you add to the pile cap. Deviation from cross-sectional dimensions. How much you can have more than the pile diameter and how much you can have less than the pile diameter. It says here you are allowed to have minus 12.5 to plus 50. But in fact, you need to keep the 100% of the area anyway. Whether you have a smaller dia, bigger dia, the area should be 100%. Reinforcement tolerances, we have a cover problem. So concrete cover measured perpendicular to concrete surface. So from the concrete surface to the edge of the reinforcement. That reduction in cover should not exceed 12.5. Reduction in cover should not exceed third of the specified concrete cover. In 336.1, 2001, concrete cover minimum was 75 millimeters. And while you're moving the casing, taking the casing out, you should not cause any shift to the reinforcement more than 150 millimeters. In 336.1.24, the cover now is having two values, 75 millimeters or 4 diameter of the maximum diameter of the aggregate. This is if you have a liner. Liner means casing like that. If you have directly soil, so from the soil to the reinforcement should be more than 4 times the maximum diameter of the aggregate, or 100 millimeters. This is new, 2024. They moved to 100 millimeters. It's not 75 anymore. And this one, by the way, it's 80 already. If you have 20 millimeters, the maximum diameter, this is 4 times 20, 80. Spacing of transverse reinforcement, 75 millimeters, or 1/12 of the width. Of course, 75 millimeters is impossible in piles. Nobody is following this, especially ACI 318 will substitute this with other ways of transverse reinforcement spacing. For me, I'm not sure if this should be applied or not anymore. In 336.3 2014 splices, no more than 50% of the bars should be lapped. This is a mistake that we all had it before, and we may continue having it if we don't recognize that we need staggering when we are overlapping. So when you have bars to be overlapped, you need to overlap not in this way. All the parts are overlapped in the same zone. No, you should lap one here, then the next one there. Maximum you can lap in one zone is 50% of the bars. Why we didn't have problems? Of course we don't have problems, because after 12 meters, the moment is almost gone. That's why the piles are surviving. Concrete strength in ACI 336.1 2024, they say every average of 3 consecutive strength tests should be equal or exceeds the 28-day compressive strength. That means if you have 28 days, you have 40, 45, and 50, and yours is 45, the characteristic design strength. So it's fine. The next 3, you can even take the 2 from this 3 if you want. So every consecutive 3 tests should give an average of the characteristic design. Of course, this is too much. You can take 3 by 3, every 3. But you should remember the batch number and age of testing and pile numbers that were cast with that concrete. Having a pile log is very important. No strength test results falls below F sub C prime by more than 3.5 MPa if F sub C prime is 35 MPa or less. So 35 or less, you should not have a deviation from the characteristic strength more than 3.5, minus 3.5 MPa. But if it is above 35 MPa, then you go with 10% of F sub C prime. So if you are 40, you should go with 4. If you are 50, you should go with 5. So if 50 MPa is your strength, you should not have any test result below 45. We go to structural analysis requirements. I'll go a little bit faster, maybe. I'm not sure how much time left for me.
Dr. Ahmed, we are a little above the time limit. If you can wrap it up in 5 minutes, that would be really appreciated.
If I talk 3 hours, it will not finish.
Yeah.
Axially loaded piles. We have 2 types of piles: bearing type piles and side resistance type, and the combination between them. Laterally loaded piles, we have rigid piles and flexible piles, and the factors affecting rigidity of the pile are soil rock qualities, characteristics, and contact surface between pile and subgrade. What is the interaction, I mean? Relative stiffness factor and embedded length of the pile. As much as the pile is longer, you're going to the flexible side. Contribution of piles to lateral loading. How do they share? So if you have a lateral load, horizontal load, you have leading piles and trailing piles or shadow piles. So leading piles are the piles in the front. They're facing the soil. Usually in ACI 336, see, this table is not a standard for everywhere. This is ACI. We're talking ACI today, okay? So in ACI 336, they assume the front piles will take full and the leading piles, the trailing piles will take less until you reach 8 diameters of spacing. Then the trailing piles and the front piles becomes the same. So if you have let's say for these 9 piles, if you have 6 diameters, the spacing. So in 6 diameters, we have 0.7 for the trailing piles. So I have 6 trailing piles times 0.7 Q plus 3 Q. Q is the pile load of the front pile, leading pile, equals the horizontal G for the group. Then we can get the Q from this equation. And then you can multiply this one by 0.7 to get the load on the other piles. And you see here, this is not at G over 9 anymore. If this the spacing is too high enough, you can divide by 9. Of course, this is a hand tool, but if you use finite element methods, you can use multipliers for the piles, different multipliers. You may have shear in both directions, so you have different multipliers. And also you can add more systematic automatic group effects. You can have a look to software like RSPile or LPile. Not LPile. LPile doesn't have a group. So let's go to pile analysis, bending stiffness. I need like maybe 5 or 10 minutes to wrap up. Let's try. In pile analysis, the most important parameter that controls the distribution of moment and axial force and shear and deflection and blah, blah, is the bending stiffness. In reinforced concrete sections, the bending stiffness is not constant. As long as there is moment, there is some part of the pile is cracking, and the other part is under compression, the bending stiffness, EI, will change continuously. That's why it's very important to choose the right E, the right I, when you are analyzing a pile. In software, these are done, it's possible. Some software like RSPile, LPile, they have the capacity of changing the bending stiffness with the propagation of cracking. At the end, you can see any pile with the moment, as moment increases, you should have less EI. If moment decreases, after cracking, I'm talking now, this until you reach this one, this is a high drop here because of cracking until you reach failure. So in each load, axial load will push the moment capacity up for the same bending stiffness. At the end, you need to make for each load what is the maximum moment, and that will give you an interaction diagram. By the way, you can have a look to this article in our website, in Rock Science website, improved analysis of reinforced concrete piles in RSPile, explaining this idea and how RSPile works. This is not available in most of the, maybe it's not available in any other software. So the propagation of the cracking changes the moment of inertia. For example, this one is done by RSPile, and you can have, from RSPile, you can have interaction diagrams, three-dimensional interaction surface. You can have factored interaction diagram and the unfactored interaction diagram, and cuts at these levels, which shows at MX, MY. So this is biaxial. And the results, you can see the beam capacity ratio, which is we are interested in. The beam capacity ratio is the moment or axial compared to the capacity of the section. So if it goes beyond 1, the section is failing. This eases things for you, because if you have like 200, 300 piles and you have thousands of load combinations on these piles, and you don't know which pile will fail, which pile will stay, this immediately gives you which piles and at which section they're failing. ACI 318 in 2025 requires, or required, EI of this ACI. We are interested in columns for piles. So in this table, if you combine axial load with moments, you can use 0.7 I gross. You should be very careful about what I'm talking. These are ultimate loads, and people, they don't know this. People design and analyze with I gross. You don't need to analyze with I gross in a cracked section. So you understand now why we are decreasing the I gross here. And if you have lateral load only, like you are superpositioning lateral load analysis with axial load analysis. So if you are analyzing the lateral load alone, so you can use 0.5 I gross. This is very interesting. You can decrease your reinforcement too much with this factor. And if you have more detailed analysis, like a software, you can use the software, which changes the bending stiffness according to the crack propagation, so you don't have a problem. Now we finished with ultimate loads. I want deflections. I want shortening of the pile. What should I do? I will use, according to ACI 31825, 1.4 times the I chose there. So if I have only lateral load, I will use 1.4 times 0.5. but it's better to use with the 0.7. So I'm advising that you should use I gross for calculating deflections, and you should use 0.5 I gross if you're analyzing only for lateral, and you use 0.7 I gross if you're combining the loads lateral and axial in one analysis. Like this one is an old sheet of mine, but you can see here I'm adding a factor for EI. I can put any factor I want to change the EI calculated from E of concrete and I gross. Of course, E of concrete is allowed by all the codes, but you can also increase that E a little bit with the amount of reinforcement by the composite section analysis. But usually it's not that much different. Why is not that much different? Because the reinforcement ratio is so small. At the end, you can combine all the load combinations in one interaction diagram. And you can see here some of the, I have two piles here. I've separated them from the whole group of piles of this type, which is type PA. These two piles, the plus and the circle, the green circle, they're outside the interaction diagram. So I needed to increase the reinforcement in two piles instead of increasing the reinforcement in the whole type. This is called PN max. Phi PN max, we will come back to it. If you have axial capacity by allowable method, ACI 318 allows you to use these two equations directly for uncased piles or cast in place piles in rock or within a pipe, but not conforming with some other provisions. I don't care. If you are designing, you can use these. You can use this always for axial load. If you have axial load only, but this, what does it mean you have axial load only? It means that your moment is less than the moment of the 5% eccentricity, the accidental one. And also it is fully supported. It's fully inside the soil, and the soil is competent. Compressive strength reduction. So if you have only axial load, you can use these factors for the strength reduction factor. These are not used for shear and moment and moment and axial. In designing piles for reinforcement, you need to know that you can decrease the minimum of the minimum. That 0.01 A gross 1% to 8%. Do you know that you can decrease this amount to 0.5% in ACI 318? In ACI 318, you can design the pile with less area and get the reinforcement required. And if the pile is successful with that smaller area, you can use that percentage of reinforcement, that amount of reinforcement as percentage for the whole area. But you're not allowed to go less than half of the area. I hope you understood this one. This is very important. Decreases your minimum reinforcement. If you go to any authority, it will tell, no, minimum is 1%. No, it's not 1%. It's 0.5% if the pile is successful with half the area. So it means like you have oversized pile just because of geotechnical requirements, not because of structural needs. Strength reduction factors vary if you have moment and axial force combined from 0.65 to 0.9. And for shear, it's 0.75. But for shear in deep foundations, for the combinations of load that have earthquake, you should go with 0.6. This is how the variation of the phi with the strain within the interaction diagram. And these are the calculations for the keynote, which from keynote you can calculate P and max that I told you, we will come back to it. And you should multiply P and max with 0.65 as a phi. So there is no other way. You cannot use 0.7, 0.75, you cannot. You can use 0.8 because deep foundations in ACI 318 are considered tied members. So 0.8, and the 0.8 should be multiplied by the 0.65. The minimum shear reinforcement is changed. So these are the new minimum shear reinforcement since 2019, I think. And you don't need shear reinforcement if your shear is less than 0.5 of the shear capacity of the concrete. This is also a new presentation of the D. D you may use 0.8 times H if you have a rectangular. This was not there before, very old before. In 2019 is there. And also you can use it as 0.8 of the circular diameter, the diameter of the circular section. There's a limit for design here. Then also if you have shear in both directions, which we usually ignore, we don't care. In the circular, you have one shear because you can rotate it. But in the rectangular, you have two shears. So if you have a barrel, you need to check this equation. And this is the new methodology of calculating the shear strength. It's not there in 2014 and before. It is in 2019 and 2025. At the end, Vs equals the difference between Vn and Vc, and Vs everybody knows it's AV FYD over S if we are not talking inclined. For piles, you are using two legs always on both sides, so the area of steel is. Other provisions to be followed are for crack width, ACI 224, durability and lifetime, ACI 365, length and development and splices, ACI 31825. I couldn't, I know it will not be enough, and I even passed my time, so I did not include these. I hope I can include them in the presentation, and this presentation will be available in geoguys.ca after like 3 weeks, maybe. You can download it from there, and the recording is with Hamzah. You can also have a look to it always. Thank you very much for your kind listening. I'm sorry I got the rights of my other colleague.
Thank you very much, Dr. Ahmed Mufti. It was really a great pleasure to listen to your talk. And thank you very much for sharing the recent advancements
Thank
in
you,
the
sir.
ACI provisions. I'm sure you will be able to advance our knowledge during the question and answer session. Our next honorable presenter, Dr. Julian Seidel. Let me introduce him. He has a long career as a geotechnical engineer. He had several positions across the industry, in construction, in academia, in public authority, general consulting, and he has more than 25 years of experience in his own consultancy. He specializes in deep foundations, dynamic pile testing, and he has provided troubleshooting for large projects across the Asia and Pacific. Dr. Seidel has authored over 80 conferences and journal papers. His most recent venture is the development of pile monitoring device, which fills a large gap in the current piling market. His presentation is based on the same new pile driving monitoring device called PDM3. Dr. Seidel had surgery, unfortunately. He may not be able to present himself. We wish him speedy recovery. Hamzah will share his presentation with us. Hamzah, over to you. Hamza, we cannot hear anything.
You cannot hear it?
At least I cannot hear it. Anybody?
Oh, let me share it. You hear it now?
I can hear you, but not the voice of Dr. Julian.
Okay.
Precision.
Hamza, we could hear the voice of Dr. Julian Seidel briefly, but it disappeared again.
Okay, let me try for the one more time.
No voice yet. Is it a separate audio track that you are playing?
No, it is no, it is included. Just let me share.
I'm Dr. Julian Seidel, and I'm a geotechnical engineer and business owner with over 40 years international experience in consulting, construction, government, and academia. I've headed my own geotechnical consultancy for 25 years. My particular areas of expertise are in deep foundation analysis and design, and in dynamic pile testing and analysis. I've authored over 80 journal and conference papers, particularly relating to rock-socketed piles and PDA testing. PDM stands for Pile Driving Monitor, which is the origin of the device. But in relation to its more general applications, PDM stands for Precision Dynamic Measurement. As you would have seen in the previous slide, it's a small camera device weighing less than 1 kilo that can be tripod mounted. In the front face here, you see the central camera lens surrounded by 4 LED infrared illuminators. Just some characteristics about PDM3. It's a high-speed, precision infrared LED tracking camera that can be used either for 1D linear or 2D area position tracking. It measures targets at up to 8,000 times per second and can track up to 32 targets simultaneously. The accuracy is 0.1 millimeters at 10 millimeter target distances, and targets can be tracked at up to 50 meters distance. The PDM3 has an onboard 6-axis inertial measurement unit, which enables a number of interesting evaluations to be made. The need for the PDM arose from my understanding that for driven piling, we have a two-class system. On the one hand, there are PDA-tested piles, which might represent 1% to 5% of the project piles, and these have high reliability and associated low risk. On the other hand, 95 to 99% of piles are typically accepted by simplistic formulas, which ultimately translate to the piles just being accepted on the basis of set alone. I don't have time to explain all the ways in which this is inadequate, but only note that the vast majority of the pile capacity estimates have significantly lower reliability and present a higher project risk. But every pile is important, and the PDM was introduced to improve the overall project reliability by greatly improving the reliability of these 95% plus piles, which are not PDA tested. It does this not only by accurate measurement of the pile movement, but importantly, also the impact force delivered to the pile. Pile set is meaningless unless you also measure the input from the hammer into the pile. The PDM results can be related to the PDA tests to ensure that all piles are driven to the same standard. The PDM provides quality assurance along with inherent safety that comes from non-contact measurement. It allows database input and output and full quality assurance reports for every pile at the time of driving. The PDM provides comprehensive graphical and numerical output as both a PDF report and summary results stored in the exportable project database file. The graphical output you see here includes both the results of the selected 10 representative blows and for the complete recorded blow sequence on a time axis. A table of detailed numerical output for the 10 representative blows is also included, and in the bottom right-hand corner, you see a preview of the PDF report. This graph compares the velocity time response for parallel PDA and PDM tests. The velocity time response is possible because of the accuracy of position measurement and the high speed of digitization. This also allows the PDM to compute peak impact force, transferred energy for offshore piles, damage assessment for every pile, hammer blow rate, and diesel hammer stroke, and ultimately to ensure that every pile is driven to the same standard as the PDA tested piles. Although the PDM has its origins in measurements of pile driving, the new capabilities of the PDM3 open up a wide range of measurement opportunities in civil engineering construction and infrastructure. These capabilities will be realised both in the current and ongoing rollout of applications. The benefits of the PDM3 also extend to vibratory installed piles. The PDM3 provides continuous tracking of vibration frequency and amplitude, penetration rate, and driving force. The PDM3 opens up significant opportunities for installation optimization with variable frequency vibrators. The PDM3 is also used for jacked pile monitoring, either for continuous records or for the final penetration validation for foundation piles or sheet installations. It is particularly useful for accurate measurement of creep under sustained test loads, which provides the opportunity for advanced verification of acceptance criteria and improved quality assurance. And the PDM can also be used to monitor piling offshore from floating barges when there is no structure or jack-up barge available. The PDM is not shown in this picture, but the reflectors on the previously installed piles are shown on the far right. The PDM3 can also be used for static load testing, both onshore and offshore. Up to 32 targets can be monitored simultaneously. A particular advantage is that the PDM can make these measurements from outside the zone of influence of the test pile and reaction system. Moving away from piling applications, the PDM is able to monitor the response of structures under dynamic loading. The monitoring frequency is 133 Hz, which is much higher than typical natural frequencies of most structures, which are less than 10 Hz. We have a rollout program for further applications in 2025, including rail monitoring, compaction control, dynamic compaction, and SPT testing. There are particular benefits that the PDM brings to each of these applications, but I will only note that for SPT testing, the PDM can deliver the energy for every blow, accurate assessment of seating distance, accurate blow counts, equivalent N values at refusal blow counts, and shear wave velocity by using the inertial measurement unit response. I want to thank you for your attention. If anyone has any follow-up questions, feel free to contact myself or my partner, Hussein Ahmadi, by email.
Thank you, Hamza, for sharing this nice presentation from Dr. Julian Seidel. Now we will move towards our question and answer session. For the sake of time and for the benefit of everyone, I have few requests. Please, if you can make one question per audience to any of our distinguished speakers, that would be really appreciated. If you have further questions and want more discussion, I encourage you to directly contact the speakers, and I hope they will be very happy to engage with you. So the question answers, we will try to wrap it up in 10 to 15 minutes. Hamza and myself both will organize the questions in taking. If we miss someone who raised their hands before and were not served, we want your apologies. We apologize in advance for that. Okay, anybody, please go ahead and ask our speakers.
I think they did ask Dr. Zahid in the chat box, so maybe we can read from there and see the selection without repeating if there are repeatable questions.
Yeah,
but one of the first question they are asking the speakers if they are okay to share their slides. This is recorded session. We will share the records, but the slides themselves from the speakers.
Okay. If someone want to ask questions from the speaker, they can raise their hand and they will be able to ask the questions. If not, we will ask our speakers.
If I can, Alessandro Mandolini speaking. I have seen a lot
Yeah.
of questions on the chat box.
Yeah,
So
we want to go to that list later on. But before, if someone has a questions in person, they can ask. If not, we will go through the chat box questions.
okay, that's fine.
Better to the chat box directly, because they already thought about it. They thought.
Okay.
Yeah.
Okay, Dr. Ahmed.
I even answered mine.
Okay.
I can throw it to the chat box also.
Okay, one of the common questions that I saw in the chat box was how the drilling method like bentonite, slurry, or other methodology affects the calculation. It is for Dr. Alessandro. How that affects the formula of calculation of the shaft resistance, or is it taken care of in that equation that you shared with us?
Yeah. But clearly, the way in which the pile is formed is influencing the skin friction, as you know. If, for instance, we are using bentonite mud or polymer, slurry, and so on, the things could be slightly changed by the specific procedure adopted. It must be said that in my experience, there is no big influence of these aspects on the mechanisms I discussed. On the final value, by sure, because is mainly reproduced by the tangent of delta, the friction coefficient at the pile-soil interface. For instance, if you use bentonite mud in a no correct way, for instance, for a prolonged time in the hole, you can have a thick bentonite filter, cake, and as consequence, all the mechanisms will develop in the bentonite interface that strongly alter the skin friction available for the piles. If you want, I can share very fastly one slide I have here. One moment here. Yeah, this is an experience made in the United States by Nata and O'Neill in '97. Is a cast in situ bored piles, and they used in both cases bentonite. But in one case, they kept bentonite for a right time, let's say, a few hours before concreting the piles. In the second one, they wanted to leave bentonite more than necessary in order to measure the effect. And you see the effect as reproduced by the beta value, about 1/10. And it is due not to the different mechanisms at the side pile-soil interface, but is due to the fact that the interface was not soil pile, but pile cake soil. So the skin friction is strongly affected, but this is the reason why I tried to speak about correctly, properly constructed piles, because the error is on the corner. But if we do error during the constructions, there is no theory able to predict our errors, unfortunately.
Thank you, Professor. There is another question that I saw, which was little surprising to me also, but it's very interesting question. It's asking about the tensile strength? Because since it will be derived, will there be any difference in the smear zone thickness if we are analyzing the pile for tension?
No, there is no difference because the development of the skin friction in tensile conditions is the same under compression conditions. There is a slight difference in the final value because there is the so-called Poisson effect on the pile. Under compression, the pile itself tends to, let's say, dilate towards the soil under compression, and so slightly contribute to increase the horizontal stress. This is not true under tensile load, but the difference is very small, of the order typically of 10%. And it is generally neglected in the design because it is in some way already considered in the global or partial factor of safety given by codes. Typically, under tensile loads, the partial coefficient for shaft resistance is larger than that under compressive loads. In order to anticipate these differences, but speaking about mechanisms, the mechanisms is the same. Pile must slide against the soil, then forming a shear bend, then dilating or not, depending on soil state, and then giving us skin friction also due to the soil stiffness of the soil mass around the pile.
Thank you, Professor. One more question was about the diameter of the pile. How do we account for, in the equation, the D factor, the diameter of the pile, if we have strip piles, for example, rectangular section or barrettes?
Okay. Sorry, okay. If we have a rectangular section, like for barrette, clearly the things are slightly different. And I personally did not have a research on it. But a lot of literature comparing the behavior along the shaft of circular section piles and rectangular section barrettes demonstrated that the value obtained for circular piles are lower, smaller than those measured for barrette. So you can use this kind of approach in some way on the safety side, because for barrette, something should be more and not less.
Great, thank you. I will briefly switch over to questions related to Dr. Ahmed Mufti. Lots of questions, very nice ones also. I think Dr. Ahmed has already gone through them. It's mostly about the questions. Let's see about this. How about lateral load due to out of verticality in case of barrette? Dr. Ahmed?
If we are talking about the percentage, the same percentage will apply. So it's related to length. It's not related to diameter. So that's easy to apply. It's, for example, 1/75. 1/75 is depending on the length. So if you apply 1/75 in each direction, you will get a shear in this direction and a shear in that direction. It depends. We cannot say don't assume inclination in this direction. You should assume the inclination in both directions. So you will have shear in this direction and shear in that direction. I understand the question is very important because if you have a diameter, so inclination in any direction will give you one single 1/75 or 1 over any value from the tolerances that we have talked about. The problem in the rectangular, if you apply 1 over 75 in one direction, then 1 in 75 in the other direction, you will like you're like adding the resultant of 2 shears in both axis directions to the pile. I have no detailed statement in any of the ACI committees and codes I had talked about, but my opinion is you should apply. You should apply in both directions.
Okay, thank you, Dr. Ahmed. Your comment is requested on a question. It says that 50% of, it's about overlapping. Maximum 50% of reinforcement at the same level. This rule cannot be applied when you are installing reinforcement in long piles because you cannot lift all the pile cage in one go, which will be necessary if the overlap is staggered. Please comment.
We're doing it all the time. That was my answer. Whether you are lifting all, you're not lifting all, that's another problem. But we do this staggered overlapping, and I did a couple of projects in UAE, and the consultant forced me to do it. Not only I chose to do it, but it was by specs. I need staggering, and also if you have ample space, ample spacing between the bars, I think then we can ignore this provision. But ACI requirement is this, so we are talking ACI requirements. If you go to Eurocode, maybe you will find something else, but ACI asks for staggering. It is mainly because of the congestion of the reinforcement in one single zone. That's why.
Yeah.
The other question, you want me to read it?
Yes, please. Yes, please.
Yeah, the other question was on the issue of spacing of spirals to a maximum of 70 or 75 millimeter. This rule is contradicted by the rule that edge-to-edge spacing between reinforcement to be 4 diameter of aggregate or 100 millimeters. Yes, of course. That's why I said when I was talking about it, I said I'm not convinced with this one. The spacing anyway is clear between reinforcement. So if you are comparing maybe 80 millimeters, 75 millimeters, maybe you can say they are all similar. If you assume the 75 center to center, yes, it's contradicting. That's why we have gone through many ACI codes and committees to see how different they look to the matter. They are not unifying their approaches through all the committees. The third question was on the issue of pile groups taking horizontal loads and the fact that the first row of piles taking the load alone. This makes sense when discussing passive resistance. It can be overcome and improved if triangular redistribution of piles is adopted, but the flexural stiffness of all piles in the group can be mobilized. Please comment. For me, what I know and what I believe is that even if you have a triangular distribution, still the shadow piles, the retail piles will get less load than the front piles. Of course, the first row after the front piles, which is in the middle of the spacings of the piles of the first row, maybe it takes more than the other shadow piles. But anyway, we can't depend on that. You can go in this case to another way of calculating the group effect. You don't need to use the hand tool. You can use systematic automatic methods. So there are several methods. Like we adopt one automatic distribution of load on piles in group in R pile. You can see it in in our overview documentation in our website for RS pile. It depends on the distance between every pile and the other piles. So it takes the effect of every pile on all other piles. And that will take this into account. Thank you.
Thank you, Dr. Ahmed. I know it's a very interesting discussion and it will take forever. We would like to take forever to discuss questions with both of you. Hamza, Dr. Julian is here with us.
I think he said he will. Yeah, he said he will be.
Okay.
Yes.
Any questions you saw about his presentation? I did not see any.
I have not a question. I have a request. I want to see the setup for the test that passed through the presentation very fast. I wish if I could have a look to it again. But I don't want to bother the people here. Maybe later I can get it from him directly.
Yeah, I'm happy to share my presentation with you and to share it generally with Hamza.
Yeah, thank you very much. That photograph is very nice one. I like photographs of testing.
Good.
Dr. Julian, I have a question about the presentation. You mentioned in one of your slides that the frequency of the structures are about 10 hertz, but the frequency of the equipment is about 133 hertz, which is more than the frequency of the structure. So is it the structural fundamental frequencies you're talking about, or is it the loading frequencies that are coming from traffic or metro or things like that?
It's the fundamental frequency of the structure I'm talking about.
Okay.
So you want to be able to differentiate the response of the structure to the passing load, and by being able to have a high enough frequency above the natural frequency of the structure, you can separate those effects.
Okay, thank you. By mechanism, this device works by lasers or by some other high frequency electromagnetic waves? And is it basically functioning like a accelerometer more or a strain gauge more or both?
It's only measuring position, and it does that using infrared LED. So you attach targets to whatever you're trying to measure, whether that is, for instance, for a pile where you're just looking at one-dimensional movement, or for other tests where you're looking for two-dimensional movements. It just tracks the movement of the targets. And in one-dimensional mode, it can do up to 8,000 hertz, and two dimensions up to 133 hertz.
Okay, so basically, it's like a strain gauge functioning. Deformations, it is not strain gauge actually.
No, it's not strain gauge. It's just measuring position.
Correct.
But if you are having multiple targets, you can determine the difference in the position of the two targets and therefore infer a strain between the 2 points.
Correct. Okay, I got it. Thank you. So, any more questions from the audience or in the chat box? I think there is one for Dr. Julian. No, Dr.
Alessandro.
Alessandro.
Yeah.
I think it is about the aspect ratio.
Mm-hmm.
I think that was the last question that I missed. Any comment on? Any comment on?
Another question.
Okay, there was another. Can you read that, please?
For the aspect ratio, Doctor, maybe you can start with, and then there is another question about the geothermal piles. What will be the impact on the skin friction as well?
Right.
Okay. About aspect ratio, slenderness ratio, no differences. in the sense that the length of pile is not influencing the local skin friction of the pile. Clearly is influencing the total pile shaft resistance, but is another problem, is a geometry problem. About the geothermal, very difficult questions, in the sense that we are collecting data in the last, let's say, 2-3 decades about geothermal piles, and the first results we are having are demonstrating that there is no so large influence of temperature cycle for the pile shaft resistance. This is particularly true for sandy soils. Maybe could not be true for clay soils because temperature can affect the mineralogy and so can affect the intrinsic soil properties. But there is no enough cumulated knowledge about the topic. What I can say is that there are many applications in the world nowadays about geothermal structures, and I can say that the problem is not geothermal effects, but is our capability to estimate fundamental soil properties like friction angle. But it's just a joke. But you understand what I mean. This is a second order of problems until now. The first problem we have is how to correctly estimate soil properties from a mechanical point of view. Then we could speak about thermomechanical properties of the soil.
Yeah.
Thank you, Professor Alessandro. I think we should be wrapping up
Yes.
our sitting today. It was really a pleasure having all of you with us. I thank you for the audience for their presence and their valuable questions. I thank you from the deepest part of my heart, our distinguished speakers, for giving us a nice insight into the state of the art in geotechnical engineering. And I also want to thank them for their engagement in the question and answer session. And we hope that we will meet in other venues soon. I would like to thank the Geotechnical and Material Engineering Committee of the Society of Engineers and the Gulf Geotechnical Engineers for organizing this event, and I hope to see more in future. Thank you from my side. Have a good day. All the best. Over to you, Hamza.
Thank you, everyone. I think we have just one remaining question for the speakers. If they want to share their presentations, we will follow up with you.
I tried to share on the chat box, but it's impossible because I am not allowed. So I will send you, Hamza, and then you will share with all the people attending the meeting.
Sure. And thank you, everyone. Thank you, Dr. Zahid, for being waking up in Canada with different time zone. Really appreciate it. Thank
pleasure.
you, Dr. Ahmed, as well in Canada, Professor Mandolini for sure. And I see also some question asking about why you don't speak about the end bearing capacity for piles. I know for a fact that Professor Mandolini has a lot of work on that aspect. And mentioning that, hopefully he will be with us in IGIC Saudi Arabia 2025. Dr. Ahmed Mufty was with us in last year, and this year hopefully we'll have them both. And Professor Mandolini will be there. Maybe he can share more light and insights on this topic, of course. So that's it from my side. Thank you. And if anyone from the keynote want to add or conclude something, please
Mr.
do.
Mr. Tawfiq raising hand. I don't know what does he want to say.
Allow Mike. I did allow you to unmute, Mr. Tawfiq.
I don't know. Let me try.
I think he wanted to ask about the presentation, if you want to share it.
No, I will upload it to geoguys.ca within 2 or 3 weeks. I need to finalize it. Maybe I will add the other items that I couldn't finish. And
Hamzah, you have my
they can download it from there. geoguys.ca.
Hamzah, you have my presentation. It's Julian Seidel.
Yeah, I do.
Feel free to.
Yeah, so Tawfiq can
share it.
No?
Okay, okay. Now this is Dr. Seidel, so he is also okay to share the presentation.
I'll send you in the afternoon.
Anyway,
Sure,
In Italian afternoon. Italian afternoon.
I can send
Take your
the
time.
one I have in hand, but let's see how it works. Yeah, okay.
Sure, Dr. Ahmed. No worries.
But you
I
have
will
the
stop
list
the
of the
recording
people?
then. Yeah, we do.
Okay.
I can share it with you as well.
Okay, thank you everybody.